just one explanation. So I was here very quick. So what I wrote down here was the problem close to Q being A. No, I mean Q being close to minus A. Well, there should be a plus here. Okay. Just I mean writing down the harmonic oscillator. Well, it's omega. So it's a frequency and then Q plus or minus A, of course. This was just one more comment. So now what we want to see is we want to calculate the classical action of the instantons. So what is the action scale, or what is the action associated with such a passage which comes in a well-defined structure, as a well-defined structure in time? So that's again still part of the first thing that was. So part A, part B, A, classical analysis. Afterwards we have to study quantum fluctuations around the classical solutions. So we found one specific solution, which was instanton solution. So let's look at the action for such a passage. So what we use is, well, we use the energy conservation here in imaginary time, which, so probably I'm here again too detailed, but let's just write down. So this was the classical equation of motion. If you multiply by QL dot and then write this like as a derivative of QL dot, and this write this using chain rule, you find now what corresponds to energy conservation in the imaginary time problem. So the kinetic energy squared, the kinetic energy minus the potential energy is conserved. Yeah. So again, we have a sign change because we are considering imaginary time evolution. So now using the energy conservation, we can then write here the action imaginary time given by the integral what we can do now, we can use that this is conserved. So Q dot squared is, I mean, so Q dot, I mean, this difference is only conserved. So if you use that Q dot classic, that this is a constant, then you can rewrite this in a way that these two terms become identical, yeah, of the form m times q classical. So we use 1, and then once we insert this identity, which we get from energy conservation in imaginary time. So here we do the same. We use 1 square root to represent this way. So why do we do this? Because now we see we have here the time integral over the velocity, and we can rewrite this as just an integral over the coordinate. Okay, so this is quite nice. We have an integral over coordinate, and this here now only depends on the potential. Okay, so if we rewrite this, then making change of variables, integrate over q here from minus a to a, because we are considering this instanton configuration, and then we have here just the integral over the profile of the potential. Okay, so this is the classical action of the instanton. This is, we define this in the following because this will appear a lot, so we want to give it a name. And this is the observation that I said before, which is actually hinting towards some topological structure. Let's right here notice that the instanton action only determined by the profile of the potential, only by the profile of the potential, and not by any specifics of the solution, so not by the dynamics or the structure, the specific structure of the solution. Okay, so to calculate the action didn't rely on any of the assumptions we used to verify that this idea of having clear structures in space is correct. Okay, so this was completely independent of this, but we have this image now in the head, and we have like these passages in time which still have the free parameter. We can shift them around, and actually we can combine various of them. We can discuss now. And the important observation here is that if we look at the classical action of such an instanton configuration, which we will need for the calculation of the path integral, this doesn't depend on any dynamical information for the solution of specific solution. It's only given by the profile of the potential. Okay? And the only thing that we used was, energy conservation. So this then leads us to the idea of the instanton gas. So far we have discussed one specific solution, but in the path integral what we have to sum is over all possible classical solutions. Okay? So again, we're considering timescales longer than this intrinsic timescale. So in this limit, we should expect that there exist approximate solutions, just using the simple arguments that we used, to the classical equation of motion, which should give that, well, all the dynamic part, I think most time is close to the maxima, so we can think about harmonic oscillators there. And then in the end, all that we need is the instanton action, which is purely determined by the potential, so we don't even have to look for better solutions. The physics should be okay that we found in this limit. So to the classical equation of motion, now this is all just to remind imaginary time, of course. All is based on the idea that in the analytical continuation. So there should be solutions which take into account several of these well-defined structures in time. And let's call them instantons, and then if we do it the reverse way from A to minus A, let's call them anti-instanton, because they can annihilate each other. Pairs. So, just make a picture. What we should expect is that the classical solutions all can be thought the following way. So here we have the timeline, here we have the coordinate A minus A. So we are interested in from configurations that start at minus A and at time 0 and stop at A at time tau. But then, like the image that, well, to stay there, you stay at minus A, you can make a transition, then you stay there, but then you can bounce back and stay there, maybe a little longer, bounce back, bounce forward, bounce back. Of course, you should end here. So you can have a combination of passages from minus A to A, which are the instantons, and in the other way around, so the anti-instantons. So we come to the idea that the classical solutions can be thought of these kind of well-defined structures which we can put any point in time. So we saw this. This is no microscopic information of this kind on the solution enters here. We don't need to know it. And the only thing that we have to do for the calculation of the action, well, we only have, if we set energy to 0 at the maxima, then you don't accumulate any action here. So the only action that you accumulate is by summing the actions of these individual passages, which we can think of like particle things. Okay. So what we then have to do to perform our semi-classical analysis, well, we have to sum over all classical paths connecting A minus A in time tau. So what we have to do is we have to do a sum over these instantons. Okay, so that's the idea. So this is kind of classical solutions, and we have to sum over all possible instantons and anti-instantons. Of course, in the end, we have to have one instanton more than anti-instantons, and they always change each other. I mean, you cannot have two instantons; they all exchange each other. And then we have to consider quantum fluctuations around these solutions. Now, what we will do is that the main contribution, and this is now an approximation that we have to verify in the end, is where still, I mean, we can have several of them, but the main, like the most important solutions are those where we can think of the particle sitting, like, again, this is all imaginary time, but in the end we're talking in real time about the particle being stuck at one of the minimum, and sometimes tunneling forth or tunneling back, tunneling forth, and this is like the short tunneling moments. Most of the time it sits somewhere here. So what we think, still physically, you can have many of these instantons, anti-instanton pairs, but what we think of is that they're still, once they tunnel, they will be stuck for some while and then tunnel again. So we will think in a way of a gas of instantons and anti-instantons, however, which is dilute. So it won't happen. I mean, most of the relevant contributions will come from, well, particle tunneling, being stuck, tunneling back, and not tunneling and immediately tunneling back. So we can think of these structures not coming too close to each other, so we can think of a dilute gas of instantons. So this will be an approximation that we do that will be verified self-consistently, and of course you can later on improve this. So maybe I just write down some of the things I said, but this is then the program that we have to do. So we have now identified the classical objects that appear in the semi-classical treatment, and we have to make a sum over this dilute instanton gas and consider quantum fluctuations around it. So just write some things I said. So according to the general philosophy of behind the semi-classical approximation, we now should sum all these solutions, weight every solution with the classical action and fluctuation part. So that is sum all instanton, anti-instanton configurations connecting minus A to A in the imaginary time tau. And this is what we call the instanton gas. And then is the second observation, it's like the intuition that we have, and this should be self-consistent, verified assumption to be verified in the end, self-consistently. Maybe I just say, so the particle, I said, will stay most of the time, or will be most of the time stuck in one of, I mean in real time, one of the minima. So doesn't like widely bounce back and forth. So we will talk about the idea that this gas of instantons anti-instantons is in fact a dilute gas. So you don't have to consider interactions between them. Okay, so in the end what we can do is we have to find the action for, let's say, such a configuration. Well, it's just given by the sum of the individual passages. Okay? So this is the main idea. So now what remains to be done is to implement this technically. So we have to write now the path integral for the transition amplitude in imaginary time in the semi-cluster approximation as a sum over all instanton, anti-instanton configuration, which start at -a and go to a, and then weight each such a contribution by the action, which we found is independent on the dynamical information of such a passage, but just contains the potential. And we have to study fluctuations around the solutions, and in the end sum everything, do the sum over these well-defined structures in time, so like topological structures, actually which doesn't depend on dynamics, and see what we get from this, and see if this has anything to do with the very simple model that we had in the beginning, where we said, well, transition amplitude should be in a periodic function given by sine squared. And yeah, so that's next lecture. Okay. Questions? Okay. Aí a gente vai, então, a próxima aula a gente vai terminar isso.